morning, everyone. So today we will talk about, well, not about computers, we will talk about the simplex algorithm once again. It will be slightly different from what we talked about well, in the beginning of the course. Not much different, but still a little different. So the main point that I'll try to convey today is basically you don't have to store the whole tableau at each step. So you remember that in the simplex algorithm we have more or less the following ingredients. At each step we have some variables which are already basic for us. We look whether we can improve the objective function by making one of the basic variables leave the basis, another one enter the basis. If we can do this, well, we do this procedure, update the tableau, and repeat the procedure once again. We have a basis, we have the non-basic variables, we see whether we can improve by making one of the basic variables go to 0, another one increase, so one of them leaves the basis, another one enters the basis, and we repeat this procedure. And at each step of this process, well, we have another table, a large matrix, large table. And what I want to do today is will describe a way of kind of partially completing this matrix. And the most important ingredient here will be the following observation. So it will be about kind of the plan for today. Given a problem, and a basis, which means the set of indices or the set of variables which you want to make basic. The set of variables reconstruct the table. So a priori it seems to us that, well, we follow the algorithm and each next table follows from kind of a pivoting operation on the previous one in the simplex algorithm. But today we'll see that there is another way. You can just trace what happens to the basis in each step, just look at the set of indices. Say x1, x5, and x7 are the bases. Well, only from this information and of course the formulation of the linear programming problem, you will be able to reconstruct the whole table at this step. In fact, it gets even better. You can reconstruct not just the whole tableau, you can reconstruct, well, in this case, less is more. You reconstruct part of this table, which is important for choosing what to do on the next step. And this will be called the revised simplex algorithm. And especially on kind of large problems, or even better, large and sparse problems, where we have lots of zeros in the initial formulation of the problem, it performs vastly better than the usual simplex algorithm. So we'll discuss all these topics. For now, let's consider an example. So I like to start with example, and then we'll leave the theory that explains this example. So suppose the linear programming problem is as follows. x1 plus 2x2 smaller or equal than 6, x1 plus 5x2 z, which is 3x1 plus 2x2. And the question is how the table looks like. If x1 and the select variable for the first constraint are basic. So the question is, we are given this problem and we know that we are going to solve it using simplex algorithm. What we want to know is not exactly the solution, we just want to know what happens, how the simplex algorithm looks like when you reach the stage when x1 is basic and the variable, the select variable corresponding to this constraint is also basic. And the other two variables, x2 and the select variable corresponding to this constraint, are non-basic. So that's the question. Well, so first of all, let me formulate this problem using the select variables. I mean, at least we will need to introduce the select variables if you want to make them basic. So one of them basic. So first of all, just reformulation of this problem. 3, 2, 1, 0, 1, 5, 0, 1. So these numbers correspond to coefficients of x1, x2, and let's say x3 and x4 will be the names of the select variables. So we want 3x1 plus 2x2 plus 1x3 plus 0x4 to be equal to 6. And you want 1x1 plus 5x2 plus 0x3 plus 5x2 to be equal to 7. Let me write not the short form of this table. Usually we would write just these numbers and leave the variables. Let me use the whole formulation that we learned in linear algebra. I'll take this matrix, multiply it by the column x1, x2, x3, x4. Once you multiply it like this, you know that 3x1 plus 2x2 plus 1x3 plus 0x4 is equal to 6. And similarly, the second row times this column is the linear combination x1 plus 5x2 plus x4, and it should be equal to 7. So what happens here, which variables are basic and which are non-basic in this formulation?
The last two are.
The last two are basic, yes. How do we know? Well, we look at this table and we see we have an identity matrix here. So basic variable is characterized by the following thing. If you have a column with just one number which is 1 and other numbers at other positions are 0, well, we know it should be a basic, part of the basis. And also, well, let me write z. It is such a thing, so let me write that this is 3, 2, the coefficients of x3, x4 are 0, and I can write it once again as a matrix product. It's this vector times x1, x2, x3, x4. And once again, another clue that x3 and x4 are basic, they have 0 coefficients in the expression for z. Okay, now what I want to do? I want to find the table, which means basically the set of these coefficients, and these coefficients, which corresponds to the situation where not x3 and x4 are basic, but rather x1 and x3. So I will want somehow will want an equivalent problem of the form, well, if I want x1 and x3 to be basic, I'll better put the identity matrix at the positions of x1 and x3 and some numbers, some coefficients for x2, x4. Well, times x1, x2, x3, x4 will be equal to something, and I want to maximize z, which is, well, maybe some number, but plus something of this form. Zeros for coefficients of x1 and x3, and some numbers for coefficients of x2, x4. So for now, I basically did nothing. I only tried to explain what does it mean that we want these variables to be basic. It's just we want kind of patronage. Once we have an equivalent problem of this form, we know that this is the answer. What do I mean by equivalent? Well, over there I have a system of linear equations. Once you have a system of linear equations, you can formulate it in different ways. Say, you have these equalities, two equations. You can take the first one and the sum of first and second one. You know that this system is equivalent to the original one. More generally, you can take this system and multiply it by any invertible matrix. Once you know, well, so what do we mean by equivalent? System. Well, if you have a system like this, AX is equal to B, so that's quite a general linear system of equations, is equivalent to, well, any matrix of any system of this form. You can multiply both sides from the left by any matrix, but you have to make sure that this matrix is invertible, that you can go back from this system back to this system with invertible B. So every solution of this system is also a solution of this one, obviously, and once again you can go back from here to here by multiplying by inverse of B from the left. So if you get a solution of this system, you will get a solution of this one. Okay, so let's go back to this problem, how to go from that system to this one and make sure that they are equivalent. Well, we basically have an answer here. It's almost written down. We want to go from this system to this one by multiplying by invertible matrix from the left. That's what equivalence means for us. Well, what matrix? I want to multiply by some matrix so that at places here, first column and third column, I'll get the identity matrix. Let me write this in a little bit, kind of, I'll try to separate x1 and x3 from the other variables. Let me write it like this. I start with a matrix like this, 3, 1, 1, 0, times x1, x3, So this just gives me part of the linear combination. 3x1 plus 1x3. And then I'll add the part which corresponds to x2 and x4. To 0, 5, 1, x2, x4. So I started with this system of equations. Once again, make sure that you see why this system is exactly the one written over there. What I did, I just separated the variables that I wanted to treat separately, x1, x3, I want to make them basic. I separated them like this. So here, this system is about 3x1 plus 1x3. I make them first, and then plus 2x2 plus 0x4. It's exactly the same row times column, just rearranged. What we want to get to, we want to get to the following shape. x1, x3 times basically nothing, times identity matrix. Plus something times x2, x4 should be equal to something. Well, how to go from here to here? By what invertible matrix I should multiply this system to get this system?
It's inverse.
This inverse, the inverse of this matrix. So I want to make this matrix into identity. How do I do this? Well, just multiply by the inverse of this matrix from the left. So to do this, multiply both sides of this by the inverse of this matrix. 3, 1, 1, 0, inverse. So this is 2 by 2 matrix, and for 2 by 2 matrix it's very easy to find the inverse. It's 1 over the determinant, which is 1 divided by minus 1 in this case, times this minus 1 minus 1. So there is a formula for inverse of the 2 by 2 matrix, which might be a good idea to remember. I actually don't. That's why I wrote it down. I mean, I do remember it's 1 over determinant and some permutation of this with some signs. And then I make sure that a times d minus b times c divided by ad minus bc, it actually works. But anyway, so we want to multiply by this matrix. So 0, 1, 1, minus 3. Yes. So let's do this. Let's take this equation multiplied by this matrix. So the first matrix, of course, becomes the identity matrix. So this identity matrix, once again, came about as the original matrix times its inverse, 0, 1, 1, minus 3. So that's kind of explanation for what is this identity matrix. Plus this inverse matrix, 0, 1, 1, minus 3, times 2, 0, 5, 1, x2, x4 is equal to 0, 1, 1, minus 3, 6, 7. So we almost achieved our goal. The system now looks like identity times x1, x3 plus some matrix times x2, The only thing is we should compute this. Well, it's not hard. Once again, it's multiplication of two Waco matrices. It should be very fast. i.e. well, let me write this x1, x3 plus, so here 0 plus 5, 2 minus 15, 0 plus 1, 0 minus 3, x2, x4 is equal to 7, 6 minus 21 minus 15. So we started with this system of equations, and we wanted to end up with a system of equations like this. We wanted to make sure that they are equivalent, so we wanted one of them to be, well, some kind of basically linear combination of that. One set of equations to be linear combinations of the other set of linear equations, which means one matrix should be, one system should be the other one multiplied by the invertible matrix. We knew what invertible matrix to use. It should be the inverse of the part of the original matrix, which corresponds to this identity. So basically, I separated this part, multiplied by its inverse, and I get this system of equations. Well, that's not full dictionary yet. So this is not the full dictionary yet. This is about the linear constraints. We also want to know what we are trying to maximize. So we want to maximize Z, which we know is as follows. It's 3. Let me once again separate the part which involves x1, x3 and the part which does not involve x1, x3. So it's 3, 0 times x1, x3 plus 2, 0 times x2, x4. So I want to maximize this linear function, 3x1 plus 0x3 plus 2x2 plus 0x4. Well, that's not how I want it to look like if x1 and x3 are basic variables. What should happen if x1 and x3 are basic variables? How should the function I'm maximizing look like? What should be the coefficients of x1 and x3? 0, yes. So if x1 and x3 are basic variables, I want them not to appear in the function that I'm trying to maximize. So how do I achieve this? How do I get rid of x1 and x3 in this expression? So in this expression, yes, so except right here we have an expression for x1, x3 in terms of x2, x4. So we can just use it. So we have the following. x1, x3 is in fact 7 minus 15 minus 5, 1 minus 17 minus 3 times x2, x4. So the linear constraints tell me you can express x1, x3 in terms of x2, x4. Now just substitute it into this expression. So Z is in fact times 7 minus 15 minus 5, 1 minus 13 minus 3 times x2, x4 plus 2, 0, x2, x4. And now we can try to open the brackets. So this time this is 21. This times this matrix is 15, 3, x2, x4 plus 2, 0, x2, x4, or in other words, 21 plus 2 minus 15 is minus 13, 0 minus 3 minus 3 times x2, x4. So now we have the full table. So if you want the table, where x1, x3 basic is, so I mean, basically it is this one. If you want to write it in our standard form for a table, you'll just put these coefficients in the right places. x1, x3 will have the identity matrix. x2, x4 will have this matrix, 5, 1, minus 13, minus 3. The coefficients on the right will be 7 minus 15. And what will be z? Well, z minus 21 will be minus 13 x2 minus 3 x4 and 0 times the other variables. So in this example, well, what was important? The important parts were, I would say, two main ideas, maybe 2.5 main ideas. One important idea was, if you want to make a certain set of variable basic in the table, it means that in this table, the part of the table which corresponds to just these variables, these coefficients, will form identity matrix. That's important. Another idea, to get from the original table to this table, you have to multiply by invertible matrix. Which invertible matrix? Well, you want to make some part of the original table into identity matrix. So you have to multiply by the inverse of this part of the original table. And maybe the third idea was, once you have this part of the table right here, it's very easy to find out what is the objective function in terms of the non-basic variables.
Why is the existence of inverses guaranteed?
It's not, but so in general, if you take a random set of indices, it doesn't have to be invertible. But the simplex algorithm, I mean, if you change the basis only according to the rules of simplex algorithm, then you'll only move from invertible parts to invertible parts.
Okay.
Because basically you're making, well, kind of subtracting some rows from other ones, so this matrix will look like, and the transition matrix from one stage to another one will look like one on the diagonal and something above the diagonal, so it will be invertible. For instance, I mean here I cheated a little bit. I chose a basis which did not come from application of the simplex algorithm. How do I know? Well, on the right side here I got 7 and minus 15. This minus 15 is not good. It tells you that x3 is minus 15, so it's not feasible. Simplex algorithm itself will never produce the basis x1, x3 here. But nevertheless, I can move to this basis. Okay, so let me try to develop, well, this example, but in greater generality. What happens in general? In general, if we start with a linear programming problem of the form some matrix times the column of variables is equal to some, well, vector of right hand side. So this is the form that we achieve after we add all the stack variables. We change all the inequality constraints to equality constraints, and we have just a system of linear equations, like we had over there. The set of variables should be positive. When I say that a vector is positive, I just mean that each individual entry of this vector is positive. And maximize z, which is some vector times x. So some vector of coefficients times x. And we want to get to a dictionary where, well, with a given basis, do the following. So now I'll just repeat what we did in this example, but now with vectors. So you'll see that it's applicable in the largest possible generality. So first of all, as we did in the example, I'll separate the set of unknowns which should be the basic unknowns from the set of unknowns which should be the non-basic. So let xd will consist, or rather be the column vector of variables that are to become basic. Let's say x non-basic, be the column of variables are to become non-basic. So I'll separate all the variables to two types. Ones which we want to make basic, and the other ones which we want to make non-basic. in this example, xb will be the vector which consists of x1, x3, and xn will be the vector which consists of just x2, x4. Also, I'll try to separate the original matrix A to two parts. One which consists of coefficients of the basic variables, and one which consists of coefficients of non-basic variables. So, B is will consist of the matrix whose columns are the columns A corresponding to the basic variables, and N will be the same thing for non-basic variables. So maybe let me go to this example. Here I just introduce notation that I'll be using, and I want to make sure that you follow what this notation means. So here, if I want x1, x3 to become basic, I'll just let the basic part of the unknown vector will be x1, x3. The non-basic part will be all the rest, x2, x4. The basis matrix, the part of A which corresponds to the basic matrix, will be 3, 1, corresponding to coefficients of x1, and 1, 0, corresponding to the coefficients of x3. Non-basic part will be 3, 5, 0, 1. Example. Well, we have to do a similar thing to the vector of coefficients in Z. So we have CV be part of C corresponding to basic variables. And Cn will be the same for non-basic variables. Here, if I want to maximize Z, which is 3, 2, 0, 0, x1, x2, x3, x4, then this is my vector C. The part which is basic will be 3, 0, and the part which is non-basic will be 2, 0, corresponding to x2, x4. So for now, I just did nothing. I just introduced names for separately part of the problem which is about the variables which I want to make basic, and separate it from the part of the problem with the other variables. Well, but now the whole trick is as follows. My original problem, AX is equal to B, and Z is equal to C times X. Well, it is in fact the following problem. I can separate x to basic part and non-basic part. And I can separate this expression, once again, to basic part and non-basic part. So here I did nothing. I just separated my variables to two groups. One which I want to make basic, the other one which I don't want to make basic. But now, this system of equations is very easy to make. Well, it's very easy to make the form of this system the one that I want. Basically, the matrix which corresponds to the basic coefficients, I want to make it identity. So I multiply this system of equations by the inverse of this matrix B. So it's the same as, say that all these equivalent formulations, xb plus b inverse n xn is equal to b inverse b. That's this system of equations. I just multiply both sides by the inverse of b. This will make these variables actually basic variables in the dictionary, in the table. And for z, well, I don't want the basic variables to appear in the expression for z. If I want them to be basic, well, I want their coefficients to be 0. But that's very easy. From here, I have an expression for what xb is in terms of xn. So z is cb times xb, which is b inverse b minus cb minus b inverse n xn plus cn xn. So let me write down the result. If I want to make the original system ax is equal to b and z is equal to cx into a system where, well, a known part of the variables is the basis, well, I do the following. I separate the system to kind of its connection with the basic variables and the one with non-basic variables. bxb plus nxn is equal to b and z is equal to cb xb plus cn xn. That's the easy part. The next step is, well, these things are in fact the same as xb plus b inverse n xn is equal to b inverse b, and z is, well, some number cb b inverse b. So this whole thing does not involve any variables. cb b inverse of b are just, well, a row matrix, a square matrix, and a column matrix. So this whole thing is just a number. Plus, let me write the coefficient of xn, it's cn minus cb inverse n. So I just took this thing and rearranged the table. Okay. So right here we have formulas that will how to go from the original formulation of the problem, ax is equal to b, and z is some coefficients times the variable unknowns. This formulation doesn't even have to be, corresponding to any basis. You can take it to be the original formulation of the problem, kind of, when you translate from the standard form to creating the set variables and finding the coefficient matrix. It could be that your problem to start with is of this form. But anyway, once you have such formulation of your problem, you can go and you know what variables you want to make basic. You can make them basic quite easily. Here's the answer. So if you want the variables which are in the vector xb to become basic, well, find out what is the part of A which corresponds to these variables, that's B. Find the one that corresponds not to these variables, that's N. And then this is the dictionary, this is the table. Yeah.
So are you saying that it's actually faster, say algorithmically, to do this by deciding which other variables you want to bring into the basis, perform this operation, then do that again until you come up with an optimal solution than it is to actually perform the simplex algorithm?
So, well, yes and no.
Because it seems for a really large matrix, and then the
Yes.
problem of inversion and the condition number, you don't really know what
Yes.
it is.
So in the end, I'll work towards trying to convince you that this is actually faster, but as written, I mean, the most naive thing that you will, you look at this thing, you see that you have to invert a pretty large matrix, you'll have to multiply it by another large matrix. It looks like here you'll have to do kind of, if the size of A is m by n, you have to do kind of m cubed times mn operations, or plus mn operations, so kind of lots of operations. The thing is, okay, so right here we are reconstructing the whole table. And it turns out that for actually performing the simplex algorithm, you don't need the whole table. So right here, we are reconstructing the whole table. We'll get the part which corresponds to the basic variables. It will be a large identity matrix. Part which corresponds to non-basic variables will be something. And the part which corresponds to right-hand sides, and the part which corresponds to coefficients of z. So here we reconstructed all the coefficients. And that's exactly what we're doing in usual simplex algorithm. We have the whole table at each step. The thing is, it is actually redundant to have the whole table. What do we actually use to perform the simplex algorithm? Actually, we use this row, the very last one, to decide what do we want to decide? We want to decide which variable will leave the basis. So, sorry, which variable will enter the basis? Which one comes with the largest positive coefficient in this row, and this variable will enter the basis. Then, corresponding to this one variable, we'll have just one column here, which will be used to decide which variable will leave the basis. How do we decide this? Well, we look at the right-hand sides here, we look at these coefficients, and we see which of the quotients is the smallest positive number. Once we have this, well, we know which variable leaves the basis. So basically, of the whole table, we use only small part. These numbers, and these numbers. So you can imagine that the whole table is large m by n matrix. But what we use is just kind of n plus 2m numbers. The thing is, using this formulation, we can compute just these numbers, not the whole table. And it is actually faster. So that's what I'll try to explain next. Maybe before actually going there, with this example, just to make sure that we are on the same page and we see that how this formulation translates to the example. So in this example, the table is, well, we can just copy the sensor from here. X1, X3, that's XB, plus B inverse N, B inverse 3, 1, 1, 0, B inverse M, 2, 0, 5, 1, times X10, X2, X4, is equal to, well, B inverse times B, so 3, 1, 1, 0 inverse times 6, 7. And Z is, well, this number is CV, where is it? 3, 0 times B inverse, 3, 1, 1, 0 inverse times B, 6, 7. So if you look at this seemingly complicated expression, you will see that it is actually a number. Once you multiply, say, this square matrix by this column, you'll get a column of length 2. Once you multiply a row of length by a column of length 2, you get just a number. Plus, well, Cn, which is 2, 0, minus Cb, which is 3, 0, times inverse 3, 1, 1, 0, inverse n. 2, 0, 5, 1. And this whole thing should be multiplied by x to x. So at least if you can somehow find these inverses and make them perform the actual multiplication, you can write down what the answer is without much thinking. Here's the formula. Find out what is B, what is N, what is CB, what is Cn, and here's the answer. Here's the answer. Okay. So for now, it looks like, well, as you said, it looks kind of stupid improvement upon the simplex algorithm. Instead of doing something which was theoretically quite easy, adding one row to another row, multiplying some global number, we are now complicating our lives by finding the inverse matrix of something, multiplying by some other matrices. It looks like we do actually more than we used to. But still, this, first of all, we already gained some insight into the simplex algorithm. If you want to move from the very first tableau to not to the second, third, and fourth, and so on, but say 1000th tableau, and somehow, for some reason, you know what is the basis for the 1000th tableau, well, you can. You can skip the whole simplex algorithm, which moves from first table to the 1000th, and just find out what is the 1000th. It actually happens. For example, you might start with a problem, you solve it, well, it takes 1000 iterations to reach the final tableau, you find out the answer, but now you remember, oh, you know what, one of the parameters that I used in the very first formulation was just slightly wrong. kind of not 2.5 but 2.6. Okay. One of the approaches would be, well, change the original formulations and iterate the simplex algorithm 1,000 times until you reach the final answer once again. Another idea, well, use the fact that if the original change wasn't very large, quite likely the final basis will also not change, or change just a little bit. So maybe it will be different from the original one by 1 or 2 variables. Cool. Then the idea is use the knowledge of the final basis that you already have from solving a similar problem, use the coefficients of the new problem, find out what is the table corresponding to the new problem. Well, if it turns out that it's not optimal, perform a couple of steps of the simplex algorithm. Typically, it will be much, much faster. So already just this very simple manipulation is, well, somewhat powerful. The next idea is it turns out that you can use this information, how the table looks like, to perform the simplex algorithm, well, at least in some situations where number of variables is much larger than the number of constraints, actually faster than the usual simplex algorithm. So that's what I'll try to explain next. So the next topic will be device simplex algorithm. The idea is do not compute the whole table at each step. Maybe an exclamation mark. So in usual simplex algorithm, at each step we write down the whole table. But it turns out that you don't have to. If you just know the variables which you want to be basic and the variables which you do not want to be basic, well, you have to use only part of the table to decide what is the next iteration. Which variable will enter the basis and which variable will leave the basis. So instead, remember, at each step, remember the basic variables, compute the parts of the table that are used to find the leading candidate. The entering variables. And we'll change the basis accordingly. So the idea is these formulas will allow you not to compute the whole table, just the relevant parts. The parts that actually are used to decide which variable is entering the basis, which one is leaving the basis. So what parts of the table are relevant? that's an easy question to answer. How do we decide which variable enters the basis? Well, we look at all the variables and we try to see whether increasing one of the variables will increase our objective function. So, to decide which variable enters the basis, look at the coefficients of the variables of the non-basic variables. In the expression for z, and choose the largest, and choose the largest positive one. So basically in the table, we just look at the final row. Z is some number plus some coefficients times the non-basic variables. Among these coefficients, we choose the largest one, the largest positive coefficient. In fact, we can choose any positive coefficient. Once we encounter one, well, it's enough. So what does it mean? So at each step, our revised simplex algorithm will do the following. We'll store the basic variables. So this will be the basic variables. We'll find out what are the coefficients of non-basic variables in the expression for z. Choose the largest entry of the coefficients of the non-basic variables in z is this one, Cn minus Cb d minus n, the largest positive. What happens if there is no largest positive? If all of them are negative. What happens? Sorry?
We already done.
Yes, if all the coefficients are negative, the largest positive entry. Yes. So if all the coefficients are negative, then we are already at the optimal solution. So this is the entering variable, entering this, the corresponding variable enters the basis. Next, I want to decide which variable leaves the basis. Well, how do we do this? Go to this board and decide which variable leaves the basis. Well, think about how you perform the simplex algorithm. Once you have the table, well, you look at the row with z minus some number being, well, some row coefficients times x1, x2, and so on. You find out which column corresponds to the variable with largest coefficient. That's the pivot column. And then here you try to find the pivot row. Remember how? You look at the right-hand side. For each row, you look at how much you can increase this variable, which means just take the right-hand side here, divide by this entry. If you get a positive number, well, find all the positive answers and choose the minimal one, choose the smallest one. So here you have the numbers, here you have the numbers, and you have a procedure which decides which is the pivot row. But we do know what are these numbers. In fact, this thing is what? The right-hand side over there, B inverse B. This thing here, well, first of all, it corresponds to some non-basic variable, because all the coefficients of the basic variables are 0 in this row. So it corresponds to a non-basic variable. How do you find the column of this matrix which corresponds to this non-basic variable? Well, the whole matrix is B inverse times n. If you want just one column of the answer, well, multiply B inverse by the corresponding column of n. So this will be B inverse times n, where n is the column of the matrix n corresponding to the variable that enters the basis. So let's go back to this algorithm. Next step is compute two things, B inverse B and B inverse times n, where n is the column of the original matrix, which corresponds to the coefficients of the variable that enters. Maybe let me formulate like this. Let me call this variable x sub n, small n, the column of A corresponding to xn. And next I want to go over the entries of this vector and this vector, take the ratios, and find out which is the smallest positive ratio. This will be the given variable. So among the quotients, J's coordinate right hand side over J's coordinate left hand side, choose the smallest positive one. Once again, initial question, what happens when there is no positive one, if all of them are negative, or all of them are 0?
Unbounded, if it's only,
Yes.
if there is a
Exactly. So this is exactly how much I can increase the J's variable. And if all of these numbers are negative, it means that I can increase each one of these numbers as much as I want, and well, it means the problem is unbounded. Sorry, it's not about how much I can increase the J's variable, it's how much I can increase xn from the constraint number J. So if each one of them tells you you can increase xn as much as you want, then the problem is unbounded. And this is the leading variable. Well, next step, repeat. So this will be our new simplex algorithm. At each step, instead of computing the whole tableau, we'll compute just these parts. This vector, which is Cn minus Cb, the inverse B. Compute this vector of coefficients. Compute this vector, B inverse B. In fact, it's a good idea to compute it first, because you'll actually use it. And compute this one column. All the rest of the table will be left uncomputed. Okay, I have just about 6 minutes, so probably not start an example of this. We'll start an example next time. Let me just tell you what kind of benefits we'll have from this. So first of all, the fact that we leave these numbers uncomputed is already good for us in terms of computations. It will allow you to compute, especially if the matrix is much wider than the store. I mean, if the number of variables is much larger than the number of constraints, you will get some improvement just by not computing these parts of the matrix in each step. You will still have to compute this kind of very long vector. It will have n benefits.
So if you had a lot of constraints, you could say for digital call.
So you will still have to compute this very long vector. I mean, if you have lots of variables, this vector will be very long. Even here you can make some improvement. You can compute just enough entries of this vector to find one which is positive. Basically, when you're computing this matrix, this vector you can compute just individual entries. You can compute it, well, kind of from left to right, or choose a random spot and compute one. So you'll be able to compute, once again, only part of this vector, not the whole one. Just enough to find one positive entry. So, yes, and also for this matrix B inverse, I mean, yes, you'll have to compute inverse of a large matrix. In some actual problems, this matrix, well, the matrix B itself is just the matrix of coefficients appearing in the original problem. In typical problems which come from applications, you'll have very, very sparse matrices, which means lots and lots of entries will be actually zero. And there are very good algorithms to compute, well, if B is kind of very sparse, how to compute in a very efficient manner such a thing. The inverse times some given value. There are algorithms which are very fast for this. So this whole revised simplex algorithm is computationally, I mean, once you try to implement it on a computer, it is much, much faster than the usual algorithm under, well, I would say, two main conditions. Number of variables is quite large compared to number of constraints, and the original matrix is pretty sparse, lots of zeros. So next time we'll start with an example of how this algorithm actually works, and I'll try to explain why it is actually computational.